Nilay Sundarkar. I am Principal Engineer at Evernorth Health Services, and I'm going to present a case study of our journey, the microservices that we have implemented over the period of 7 or 8 years, specifically focusing around CDC data pipelines, the past, present, and the future. To give a background about the company, Evernorth Health Services is part of the Cigna group. There's a company called Express Scripts, got acquired by Cigna. Now it's called Evernorth Health Services. There's a bunch of organizations that are part of Evernorth Health Services, but Cigna is a global company, presence in 30 countries, 70K plus employees, and we are committed to improving health and vitality for about 130 million customer relationships that we manage. Some of you might know Cigna is a very big insurance provider. Some of your cards might say Cigna on them. So I'm from Cigna. So real quick, I'm going to go over the agenda as to how I've broken down this presentation, so as to give you some idea as to how it's going to progress. To begin with, we are going to go over what we have today in terms of the CDC data pipelines, and this is completely on-premises, what tech stack we have used, challenges we faced, solutions we implemented, and limitations possibly as well. So the first part of the presentation would be that. The second would be what we have been doing for the last 1 or 2 years, is basically moving these ecosystems or these microservices along with the pipelines to a public cloud, which is AWS. And we'll go through some of the design patterns. That topic itself could be a talk, but I'm going to condense it, cover some of it. We're going to go through that, look at some of the interesting patterns around consumer cutover with respect to Kafka consumers. And then towards the end, we are going to look at what we are now thinking of doing in terms of what our patterns look like in AWS with the new set of capabilities that AWS unlocks. So we are going to look at that towards the end of the presentation. So that's basically the agenda, 3 divisions, past, present, future. So we'll begin with the past, but before that, I need to establish some context. So you see on the left-hand side, this is how our legacy integration approach was, where we have these mainframe systems, usually backed by DB2 databases, bunch of APIs that expose that data. And then we would have these microservices, APIs defined based on domain-driven design concepts. And they would then consume these APIs and then be used by other systems, basically. So I've represented some of them here, and we usually refer to a microservice API as an entity in our organization. So that's why you see entity A, entity B, and entity C. It's just a representation of much complex design. Actually, this is much simplified way of just establishing some context with you guys. And then these entities would then also talk to each other if needed. Now, you might know of the reasons for which people do microservices: scalability, fault isolation, reusability. We faced some of those similar problems, and this was years ago when we started on this journey. So we decided to then get on to this journey of doing a microservice with its own data store and a streaming interface. So that's what is our strategic integration approach, which started 5 to 7 years ago, basically. So in here, if you see, I've drawn a corresponding entity that I have on the left-hand side, but it has its own data store now, and it has a streaming interface as well. So it's a Kafka topic. It's MongoDB that we use generally. So similar to entity A, there's B and C, and now they talk to each other via the topics or the streaming interfaces that are exposed. Now the obvious question is, how does that data get into these entities, the entity data stores from the legacy databases? So we use a tool called Click, formerly Tunity, and the blue arrows that you see here are basically the data pipelines that kind of continuously hydrate the data for these entities from the legacy systems. The goal obviously is to move all the consumers from the mainframes or the legacy systems which were built for decades. And there's a lot of volume there. We move them to these new core systems now. But until that happens, these data pipelines are the blood veins of the data that needs to be available for the consumers that have moved to the microservices. So what we're going to do now is going to focus on the blue lines that you see. We are going to expand, dive deeper into those, and look into the design patterns that we had to solve for, or the challenges that we faced in those. So this is how a typical entity pipeline looks like today. So this is basically the past that we have already done. We are in production with this. So we've represented mainframes or the legacy on the left-hand side with a database. Then we have the microservice represented on the right-hand side, which is the data store. The tech stack is that we use enterprise MongoDB. We use Spring Boot applications hosted on Pivotal Cloud Foundry, which is PCF. Back then, PCF was one of the big players. Now it's not. So, and we'll come to that. It's part of the reason why we're moving to AWS. But that is our tech stack right now. We call it tech debt now, but it's the Spring Boot applications that you see here, the icon, those are Spring Boot applications developed in Java or Kotlin and deployed on PCF. And there's a Kafka topic that exposes the whole entity or the microservices data on a streaming basis for consumers. Then we have Click or Attunity, formerly reading the redo log or the write ahead log from DB2, writing the data to one or more source topics. Now we are getting into what the data pipeline actually does. One of the speakers mentioned before this that pipelines nowadays are not dumb pipelines. They do things, and there's complexity. So which is what we also have. So the first component that we usually have in our typical pipeline is a transform component. It transforms from the legacy format to the microservices format, usually denormalizing a normalized schema. Not such a challenging thing, but the challenge lies in getting the domain right and the modeling that goes behind it. But it is still done as part of a Java application that reads from a topic and then writes to a topic. Then we have this thing called an update processor. Does the state management, basically looks at an event which could be update, create, or delete, writes data or updates data or deletes data in the microservices data store. One of the things that I need to call out here is that that component does generate a thing called a resource ID, which is a GUID, and it corresponds to a primary key on the legacy side. So claims is an example that you all can imagine. So if in a claims entity, the primary key on the legacy side is a claim ID and a deed of service. But then on the microservices side, we have a corresponding GUID associated with that data, and then there are queries happening on that GUID, and that GUID then gets used as a reference in other microservices, basically. So the point of calling that out is that this is data that is generated by the pipeline. It doesn't exist on legacy. So it does add fair bit of complexity when we think of migrating this. So this is the typical pipeline and the tech stack that we have used, everything on premises. This is what we have in production. So just to do a logical grouping here, you see the blue group, that's what we will refer to as legacy. The green will refer to as the entity or the microservice, and the yellow is what we are going to refer to, or I'm going to refer to as the CDC data pipeline. And we are going to focus mostly on that yellow portion of this going forward. So we're going to look at what all variations we have had in that yellow box so far. So to begin with, aggregation and enrichment, you can imagine what this could be. But there are several ways we did this. Click, for example, can do a join from the source table. So if you're getting a CDC feed for a single table and you want to join that data with another table, Click has the ability to go and query it and then enrich your stream or add that data or field to it and then send it to you. The drawback obviously is the latency that it introduces of going back to that other table and getting that data. The other way we did this aggregation was doing some windowing using Kafka streams, and primarily aggregated events based on a transaction ID on the legacy side. So created a perfect watermark based on which we were able to know how many events originated for a given transaction for multiple tables that we are listening on, and then kind of aggregate those in a single group, apply that change to the microservices data store in a single update or a commit. So that we have some sort of transactional consistency. It's still eventually consistent, the whole thing, but you don't apply these updates that happen as part of a single transaction separately. So that's one way of aggregating things. We did that using Kafka streams. Then there's cases of local lookups where the microservice would store a materialized view of another microservice and then do a lookup or run some rules of validation from some other domain, and then appropriately then update, delete, or do whatever it has to do with the event at hand. And then we also had enrichment where in very few cases we needed information from outside services or databases in order to validate or to enrich the data. And for that we would make API calls or do an external database lookup. Sort of a anti-pattern to go to another database outside of its context, but in very few cases we have done that, or either gotten a local copy of the other database in that microservices context. But these were the few ways in which we did aggregation and enrichment. The next big thing that came our way as we progressed was bidirectional writes. Initially, the focus was to get the data from legacy, put it in the microservice, enable reads. That happened, we started getting more traction on the microservices, and soon enough we had the case of enabling writes on the API that we have on the microservices side. So in that case, obviously, you now want that data to be written to your entity data store or microservices data store, but that data also needs to now flow back to your legacy system, because you now effectively have created a situation where you have two sources of truth. And this is well known as the split brain problem that people have sometimes when you have conflicting merges going on from both the sides and you have no idea then which one precedes which. So how did we solve that is what we're going to look at now. A few ways that we tackled this. One was doing this pattern that we called a write-back adapter. So we recommend people to not get into a split brain scenario where they have to take care of these merges. So what some of us did was have that data go back to legacy systems, to an API via an HTTP API, and let that data come back to your data store via the CDC pipeline, causing eventual consistency again if the consumer was okay with that. But then in this manner, there's never a case of two masters. There's always a single master. Of course, there are drawbacks to this, because you eventually want these rights and the consumers to be moved to your microservice. So you don't want to use more of your legacy systems. So some of us did this, but this is easier to do. Doesn't involve a lot of complexity. Some of the microservices teams also did multi-master situations where they relied on timestamps. Now timestamps are not reliable. Depending on the system that generated it, they could vary. And when it comes to events that happened at the same time, and if the timestamps are from two different systems, you just can't rely on them. So there's that little bit of a risk or a corner case involved in case of a conflicting merge, that you would still get an incorrect state because you're not able to correlate these timestamps. So in that case, people who are able to accept that risk, they would then write it on both the systems, and when it came to merging data for updates that happen on both the systems at the same time, they would then rely on a timestamp and then compare it and then predict which one happened before, which one happened after, and then sync up the data basically. So that was another pattern we used. There's an interesting thing which came up, which was consumer segregation, where some of the writes that were needed on the microservices side and the resulting data that was created out of it was only needed on the microservice. There's never a case of that data going to the legacy, because there's never a case of people needing that data on the legacy side. So there was a proposal to use that too. I don't think that we got too many of such cases, but that was another pattern that we considered where we just write it to the microservices database and not let it go back. So then there's no case of a multi-master bidirectional writes happening. And the last one was something that we referred to as Big Bang. In very few cases, we had teams that actually owned the legacy system. Teams that were doing the microservice were also the ones that owned the legacy system. In that case, they had complete control over how they handled these writes, and they were able to write a single point where they could have the write go to both the systems and write it in a transactional manner and control basically the way the data gets written to your system. So that's what is referred to here as Big Bang, and I haven't really shown it in the picture so much, but basically having control over legacy and on the microservice is what it was. After that, before that actually, when the first problem we faced was initial loads. When we created these data pipelines, the question was how do you bring over the data that exists on the legacy into the microservice, and some of the domains really had like a lot of data, like for example, claims had like billions and billions of records. So how do we bring in those initial loads, and how do we do backfills? And we'll talk about what backfills are. But in terms of the initial seed or the initial load of the data, what we did is our preference was to use the pipeline, not to invest too much into loading the data all over again. Just use the pipeline that we have, load the data, let it do what it does. But it did not work out too well for high volume situations. So at least 20 to 25% of our microservices had too much volume on the legacy, and this did not work out. It would take weeks and months to just get the initial seed. So then if that was the case, we did end up developing these Spring Boot applications that did custom micro-batching, logically divided the source database, and then wrote those chunks basically in parallel on the target database using batch writes, and achieved the efficiency in terms of time. And again, behind the scenes, we did spend time on doing competing consumers and stuff like that. And you have to keep in mind that this is still like 4 years ago, basically, when we are still on-prem. There's no AWS in question. Then coming to backfills, backfills was an interesting problem. Once we are live and the microservices started getting used more and more, there's more demand for attributes on that domain for several reasons. Sometimes the domain modeler would miss these attributes, and then we would need them. Or sometimes there would be a new attribute that gets added to the legacy side. So in that case, the problem became that you need to now have these new set of attributes on your denormalized schema, but then you need to have data in that attribute for all the records that you have. So it's a case of an initial load all over again, but this time for only those attributes and with active consumers. So you can't just go back to your pipeline and load the whole thing all over again. So you had to do something which was sort of a simultaneous CDC and initial load mechanism. So we used the exact same two things, the pipeline or the micro-batching strategy, but this time around we had to implement some checks in terms of which event gets written to your microservices data store. So there again, we relied on some timestamps on the source, made sure that we are not writing incorrect data. We're writing the latest data. Basically, it could be the CDC event, or it could be the load event based on at what point the event was read from the source database. So these were some of the ways, some of the problems or challenges we had, and the ways we solved those in our past with the on-premises system. The last slide around our what we have already is around reliability and observability. I'm not going to spend too much time here because this is pretty standard stuff. But just to call out, the main problem that we faced was certifying our data. Now this data that we have on the microservices is critical. Patients' lives depend on these. Sometimes we cannot go wrong. Basically, we cannot afford to go wrong with this data. And for that reason, we had to do a lot of checks. So we ended up doing these reconciliation apps, which would do the data checks. For example, check the transformations that you have done, look at counts, look at how many claims you have, for example, and correlate that with the count of claims you have on the other side, for example. Also, even if the count matches, sometimes you would drop an event, for example, right? And you would have the old state on the microservices side. Then in that case, you would want to check that all of your events have made it through. So we did event checks based on certain timestamps that we had, which were like the last written timestamp on the legacy side. And we would add up those timestamps like a file checksum mechanism. So some sort of check that would guarantee that we have processed all the CDC events. In terms of error handling, retries is pretty standard stuff, what Kafka gave us out of the box. We had these retry topics. We still have them, these retry error topics. Some of us also have developed libraries using like Resilience 4J and stuff like that. But pretty standard stuff in terms of making sure that we retry a failure event, we log it, we react to it. And there are automated processes in place which will make sure that that particular record gets to the correct state. In terms of observability, New Relic is our main tool today. We send a lot of metrics to New Relic, a lot of debugging and a lot of problem solving happens with the help of logs that go to New Relic and Splunk. For Kafka, we used Control Center and also New Relic, combination of the two. Control Center isn't the most liked tool in the company right now, but it does give us the basic ability to look at the topics, the lag, the replicators and stuff. So we have that. What I forgot to call out here is the Mongo Ops Manager, which we use on the Mongo database. But those are the things that we used for observability, error handling, reconciliation. For ordering and delivery guarantees, our pipelines do use the inbuilt ability of Kafka to process a given partition sequentially. So the update topic that you see here, the one that is just before the database, we partition that topic in a way that it gets the data for a given record in a single partition. So partition by the primary key. In that way, we are able to guarantee the ordering. In terms of the delivery guarantees, we do at least once. At most once is expensive in terms of the compute or the processing that it needs, and at least once is something we cannot do. The at most once is something we cannot do. So all our pipelines are at least once in terms of the guaranteed deliveries. So those are the other factors around reliability and observability. Now coming to the present, as to what we have been doing for the past 1 or 2 years is basically re-platform these applications to AWS. As any migration expert will tell you, you need to think of moving to a cloud or a public cloud in iterative fashion. You don't want to redesign and re-architecture your existing production apps in the first go. So our strategy is similar. Go to AWS with what you have, just re-platform it, and then think of reusing some of the features once we are there with the consumers, and then think of the future patterns, basically, if you have to develop from scratch in AWS, what those look like. So I'm going to quickly go over this, not dive into all of the details, but give you enough context as to what we are doing right now. So what you saw with the past, it's going to not change too much, but now it's going to be in AWS. The other driver around this is consuming a topic or consuming a database that is on premises from AWS is considered an anti-pattern for us. And for those reasons, we need to move our infrastructure and our data along with the API and the streaming interface into AWS. So it's basically an effort where the whole microservice system goes into AWS while having an active consumer in production. Right, so the way we do that is use Kafka replicator. That replicates our source topics into an AWS hosted Confluent cluster. So it's basically a sister topic for every source topic that you have here. Then the exact same processors that we had, the transform and the update processor, we are now moving that code into AWS EKS. From there it goes into Mongo Atlas. So Mongo Atlas was the parallel for enterprise MongoDB. Use tools like Mongo Mirror to load data, to do backouts and stuff like that. And then you see the other things are also kept the same, but the container has changed. So the fact that we are on PCF was another major driver for us to get into AWS, because PCF is no longer a strategic partner. We need to get off of it. And there's that driving, to an extent, that drives this replatforming effort as well. The interesting part that I want you guys to look at is the topics at the end, the interface to external consumers. There you see a replicator replicating that data back down on-prem. The reason for that is that we might have a consumer on-prem for these topics, and that consumer won't be allowed to go to an AWS topic. So then, he just continues doing what he does, but this time the data is coming from a pipeline that is in AWS. Now, I'm not going to go over the cutover strategies. We actually explored a few patterns here. If we could do a parallel pipeline, if we could do a 1-0 cutover. I'm not going to get into that. It's a topic in itself. But this is what our AWS data pipeline looks like today. Like, there are a few that we are on the verge of migrating and cutting over. And this year we're going to move increasingly more such ecosystems to AWS. One interesting thing that came out of this effort is what I want to kind of go through in more detail is around how do you move a consumer from a Kafka topic that replicates to another Kafka topic. So if you have that case, then how do you do it? This came from a white paper that Confluent had published. And our Kafka team, some of them are here. They kind of worked with us with Confluent to get some of these scripts that would enable us to do that. So I'm going to dive into that use case. It could be something interesting for this audience. So it's basically this: if you have topic A and you have a replicated topic B, and this could be a topic in AWS or whatever. I've ignored that detail, but think of topic A and topic B and think of a replicator in between. And if you have a case of a consumer with consumer group C1 consuming data from A, and let's say you have this much data, it's at message 8,000 and it has 2,000 more messages to consume. So that's where your consumer group is shown. And then can we now move this consumer to topic B and start from where we left off, assuming all the data is synced up and being replicated at near real time, right? So can we do this, and how do we do it basically? So on this topic, you have the whole messages now, and typically when you do these consumers, you could either start from earliest or you could start from the latest. You could also reset your offsets to some number or some time, but then how do you move to the exact point if you have to? That's what this slide looks into. So you need to be somewhere in the middle, correct, for this consumer. So this is all from a white paper that Confluent published, and we actually worked with them to get a script around this, which is so if on topic A, the broker, let's say it looks like this with a offset of 23, and there's a field that Kafka has called create timestamp. So that's what I've shown here as TS equal to 1. It usually is a huge long number, but what happens is on the other broker where you have these messages being replicated, the offsets are not reliable. You cannot guarantee that the offsets for a given message or a partition are going to remain the same. And there are these reasons for that. And this is also again explained in more detail in the Confluent white paper. Like you could have garbage collection run on the source topic, you could have retries happen on the replicator, there could be a lag in the underlying offset, the topic that, the system topic that Kafka has, there could be lag on that and stuff like that. So your offsets are not reliable, but what is reliable is your create timestamps. They get copied as it is. So what you do then is you get all your offsets. You stop your consumer on topic A. At that point, your offsets are at some point on each of the partitions. You get all of those offsets. You get all of the timestamps, create timestamps for those offsets for all the partitions. You then set your corresponding offsets on the other broker using those timestamps, right? And now your consumer group, which is shown as C1 here, will point to a different offset, but it's going to start from the point where it left off at. So this is fairly complex. I mean, you have to develop scripts for this. You have to make sure you apply those scripts in a right way. You have to coordinate. So we don't do this unless really needed. The approach that anyone would usually tell you to do is just to stop the producer, move the consumer, like after it has consumed everything, move the consumer and then start the producer again. In cases where you don't have control over the producer and you just can't afford to stop it, or there's no way of stopping it, then this could be useful, where you can stop the consumer and then reset the offsets and then start consuming again from the point where you stopped off. This was something that we discovered or we went through when we developed these patterns of doing cutover for a consumer for AWS migration. Now, the last few slides, I think I'm going to go over the future, or what we are trying to do, and what our greenfield patterns look like in case we have to develop this microservice in the cloud. To do that, I think we need to go through the factors or the goals that we have in terms of the limitations that we faced when we did this on premises. And this is because several reasons. This is not just that we are aware of some of this, but there's not enough capabilities on-prem. Now with AWS, we have a lot more at our disposal. So we need to look at those limitations before we look at our greenfield approach. So the biggest problem was our developers or the microservices teams is spending time writing these applications over and over again. The time to market was just too high. There's no standardized components for these. They were writing these over and over again, and the demand was increasing, but the rate at which these pipelines were, or the entities or the microservices were being shipped into production was not good enough, basically, and it still is not up to the mark. So that is the main limitation. The other was the infrastructure that we have. Although not a showstopper, it is still not self-served. It's basically, there's an admin team that does that, and there's some level of lag that gets involved there too. So we ideally want our infrastructure to be provisioned by the teams, by Terraform or any other mechanisms. So that was the other limitation we have. And I guess what we learned out of this was that we just kept spending time on developing integration logic, and along with domain logic, we had mixed the two together. I've heard another talk where a person was saying that to be competitive, you need to have your developers focus on your business development, not on the integration, basically. And that is true. We actually felt it firsthand because we spent so much time reading from Kafka, implementing that in our processors, writing to databases, writing to another topics and stuff like that. So that was the other driver behind this. So now, how do we do that? How do we have those limitations addressed with something like AWS, which gives you more capabilities of doing things? So that's what I'm going to go through. I do need to call out that this is fairly experimental right now. We only have prototypes for this. It's not in production. The things might change for us, but the limitations of the drivers will not. The limitations that we have been through are the ones driving us, are the ones that we need to solve. So here, if you see, what I've shown is a case where we do self-managed infrastructure. We do our Kafka topics, Atlas, like database, and the topics, either through Terraform, or it could be Confluent Cloud, or it could be GitOps for Kafka as well. So that's what we are exploring right now. Atlas, we have already done. It's we have productionalized Terraform scripts and modules where we can create an Atlas cluster for a team. The team can create it for themselves, basically. And then that whole thing around separating the integration logic or automating that integration logic for the team, we are thinking Confluent connector fits that gap very well. Instead of writing that entirely in Java, we want to do a Confluent connector based integration with various sync and source connectors that they have made available. So if you see this box that I've drawn here, it's basically the integration layer more so, that basically should be available for a team at the click of a button. Basically, it gives them that skeleton of the whole thing, and then they do need to inject their domain logic in these integration points, right? So how do you do that? And we are not trying to solve for automating the domain logic completely. That's practically impossible to do it. But then so that's why we see lambdas as a very possible use case where this connector then makes a call to a lambda function, which kind of gives you the ability to have your own custom rules specified. So you give it an input, it converts it, and it expects a generic output that then goes to the next topic, basically, right? So in that manner, the green box that you see here, that's basically the domain layer, and that's where we want our developers to focus more time on. The layer below is what we want them to kind of get started with immediately, like with the click of a button, but yet have the ability to customize it or to change it or tweak it a little bit. For example, if they want to use only one connector than two, or if they want to increase the partitions or decrease the partitions, stuff like that. Even in the green box, there are efforts going on where we are trying to componentize these things, like transform processor, for example. There are libraries that we have created which can be driven just based on configuration. So then that becomes even more scalable. Same with the state management machine, for example. There are efforts at trying to see if we can create a linear workflow kind of a thing which is configurable, at the same time not driven by something like a workflow engine, or something that runs within a Lambda or something. So there's effort around that green box too, to kind of make it more configurable. But this is what we think that would solve our problems that we have faced on premises, and this is what we are embarking on now for the last few months, and we are on this journey now along with our partners in the organization. So that ends it. I'll go over some of the 3 takeaways actually for us and for anyone who relates to this. It could be relevant to you. One is if you can, follow the enterprise integration patterns approach of separating out integration logic from domain logic. There's this book written by Gregor Hope. It's written in 2003. It is still very relevant, and it's a golden advice that he has given there somewhere, where he says you don't want to have these two mixed. Basically, you want to separate those two out. We kind of did not do it too much, but we are now trying to do it. So if you can, you should follow it. Second, this is just no-brainer. Basically, any migration expert tell you to go step by step into the cloud. So, and we pretty much did the same. We are, moving into cloud and then changing it a little bit after we have moved, and then completely redesigning it for newer applications. And lastly, if you have the same tech stack, use of Confluent Cloud or GitOps or Kafka or the schema registry, which I did not talk about, but these things have so many features that Confluent developed for us that you don't have to reinvent the wheel basically sometimes. So better to look for a Confluent connector than developing Java for the same thing. Some of these mistakes we have done, like we have written custom code for things which we could have saved time on. So that could be another takeaway if you have a similar tech stack and a similar system. With that ends my presentation. I can take any questions if anyone has any. Thank you.